Okay, so in this particular video, we have a car that starts at rest and it accelerates uniformly, and it covers a certain amount of distance x in a certain amount of time t. Okay, so here's the diagram. It says that the car starts at rest when time is equal to 0, its initial position is equal to 0, and here's our reference point. Based on the wording, it says that the car covers a certain amount of distance x. We don't know what x is, it doesn't really matter, in a certain amount of t. Okay, so whatever t is. So this is our reference point. Usually the problem has to give you enough information to have a reference point or a baseline. All right, so let's do it. Here in part A, B, C, and D, and E, it asks us just to find the ratio of these x value, or aka instantaneous position at these particular time value compared to where it is at time t. All right, so if you need to, pause the video, copy it down, write it down, do whatever. All right, keep up. So here's our reference point, as I stated earlier in the purple box here. Again, the problem states that it covers a certain amount of distance x and a certain amount of t. I don't care for what these values are. That's not the point of these types of problems. It's just to see if you can predict what the outcome is if you actually know the value of x and t. All right. So here I have my displacement function, which is equal to VIT plus 1/2 AT squared. The problem starts at rest, which makes things easy. So I want to cancel that VIT term out in this particular function because it doesn't really matter. Therefore, what I did was I replaced delta x with x here. Well, you could call it delta x if you want, but the diagram and the wording suggests that it's just some distance x. So x represents your distance to the right, whatever that is. All right. So in order to find distance, you need to know what the acceleration and what the time is, and we just square that time function. So here we have distance, aka x is equal to 1/2 AT squared, and this is important. This is what I call a baseline or a reference point. All right, so everything's going to be compared relative to this particular statement, the given stuff in the problem. Let's knock out part A. Part A asks us to find the distance at 1/10 of the time. So if you look at part A in red here, it says what is the distance. Again, x here is representing distance, not displacement. How far did the car travel in 1/10 of the time relative to what's given in the diagram? We know that at time t, it covers some amount of distance x. But here, it wants us to know how far did it cover 1/10 of the time. All right. So therefore, we can set up the same function here. Here I have the statement that I just carried down for part A. How far did it cover in 1/10 of the given time? Well, common sense tells you that it has to cover a shorter distance because it hasn't traveled time t yet. It's a fraction of time t, so therefore the value has to come out less than x. All right, so let's do it. Here, I just set up my displacement function relative to the reference position here. Again, delta x is equal to VIT plus 1/2 AT squared. Here, instead of calling delta x, I just call it x at 1/10 of the time. VIT 1/2 A, and then for t, I just substitute in for 1/10. But you notice here I use parentheses when I do my substitution. It's important that you use parentheses when you do substitution, especially when there's an exponent on the outside. All right, so I know VIT is 0, so therefore I can simplify this particular function down. It's just 1/2 AT over 10 squared. But this exponent needs to be distributed. So here I made a note for you. You need to distribute the exponent. So if you don't write stuff with parentheses, you are going to fall for algebraic traps, or sloppiness I call it. All right, so because the t over 10 is inside of parentheses, you need to distribute this exponent square, or 2, to the t and the 10. So therefore, if you do that properly, you should get 1/2 AT squared, because t squared, and then 10 squared is just 100. But you notice here I highlight everything in black for you. The 1/2, the A, the t squared in black is what we have over here on the left side, our reference point. 1/2 AT squared is x. So wherever 1/2 AT squared is, I can just substitute it for x. I can replace it for x. But here, I notice that the only thing difference from this reference statement to this red part A is the 100 in the denominator. So here's the 100 in the denominator. So in that case, I can just factor out the 100th in front. So the 100 I kept on the bottom, and the 1 on top, just make sure that it's the same or proper fraction here. Okay, so therefore I can keep 1/2 AT squared as a single term. So if you're keeping up right now, 1/2 AT squared is simply x over here on the left side of the screen that I'm circling. So it's important to write a reference point, and from there your work is referencing that particular statement. So here I know 1 half at squared is equal to x. So wherever I can factor out 1 half at squared, I can substitute it in for x. So here I just kept a 1/100th in the front, the coefficient in the front the same. But instead of writing all this 1 half at squared, I can simply substitute in for x because it is equal to x. That's what's given in the problem. So 1 times x is just x, and then divided by 100, which is just 100 on the bottom. So our answer is 1/100th of the distance, okay? So why it only wants us to find a tenth of the time, the distance covered is actually 1/100th of the distance. All right, so let's do part B. Part B asks us to find the distance covered in 1/8 of the given time. All right, so here I carry the same statement down, and I'm just going to follow the same process, so hopefully you keep it up here. Here, x of 1/8 of the time, VIT is 0, because I'm just going to cancel it out. Wherever t is, I'm going to replace it t over 8. Again, use parentheses and distribute the exponent to t and the 8. If you do that properly, you'll get 1 half a t squared. 8 squared is 64. And here again, I've highlighted everything in black here. That matches my reference point. 1 half a t squared is x. So therefore, I can factor out this the 64th in the denominator out in the front. Okay, so it looks like this: 1 over 64, and then I can just rewrite the 1 half a t squared in the back here, or following that, and then 1 half a t squared is just x. If you kept up with part A, if not, rewind a little bit. 1 half a t squared is simply x, because that's what it says here in the reference point. And so I can replace 1 half a t squared, which is x, which equals to 1 over 64 times x. But 1 times x is just x over 64. So that would be our answer. So traveling 1/8 of the time covers 1/64th of the time, because the function here is a quadratic function. So it's important that you can go forward and backward. 1/8 of the time would correlate to 1/64th of the distance. If you were to do 8 times the time, it actually would cover 64 times the distance, okay? So listen to that again if you need to and write it out. All right, let's do C and D. Here, C is pretty much repetitive of part A and B, but hopefully you're keeping up and this makes things easier. It says, what is the distance traveled during 1/4 of the time? Okay, so we can set up the same steps, cross out VIT, because VI is 0, and wherever t is, I can substitute in t over 4, distribute the square to the t and to the 4, so 4 squared is 16, and this is where I have 1 half a t squared over 16. The 1 half a t squared on the left side, our reference point, tells us that it's equal to x, so therefore we can just factor out the 16th in the denominator on the front. I'll keep the 16 in the denominator, so by putting a 1 over it, doesn't change anything. So therefore 1/16th of 1 half a t squared. We highlight the 1 half a t squared, which represents x, so therefore our answer is just 1/16th x. Okay, 1 times x is x over 16. So that's our answer, which makes sense, because if you were to travel 4 times the amount of time, well, 4 times the amount of time actually suggests that you would cover 16 times the distance, because 4 squared is 16. So if you actually travel for 4 times the amount of time, in physics here, if an object accelerates, you would actually cover 16 times the distance that it covers. So you should be able to go forward and backward. Here in this part, it says 1/4 of the time. Well, because it's 1/4, well, squaring that coefficient allows me to figure out that it's 1/16th of the distance given. All right, so therefore the answer here is 1/16th of whatever x is. All right, let's do part D. Part D here is a little different. Instead of finding a fraction of time, it's some multiplier time. So if you kept up with my verbal in the previous example or in the previous part C, we already know what the answer is, but I'll set it up properly here for you. Here it wants us to find the distance covered during 4 times the amount of time. Okay, well, let's just set it up. X is equal to 4t, or x of 4t. VIT crosses out, 1 half a t squared. But here, instead of t, I replace it with 4t, because that's what part D is asking for. How much distance did you cover if you were to accelerate for 4 times the amount of time? Well, distribute the exponent to the 4, which gives us 16. Distribute the exponent to the t squared, which makes it t squared. So therefore, we have the statement, 1 half a 16 t squared. Everything I highlighted in black here, or color coded in black here, 1 half a t squared, is simply x. Okay, Therefore, we can factor the 16 into the front. It will just have 16 times 1/2 at squared, but 1/2 at squared is simply x. So therefore, our answer is 16x, because your displacement function is a quadratic function if an object accelerates or decelerates. All right, let's do part E. Part E asks here just some random time interval, okay? How much distance did it cover after 4.2 times the amount of time? Again, it can be 4.2, 4.8, 5.2, 6.8. It doesn't really matter. You have to learn how to do this process. All right. Therefore, I have here x is equal to x of 4.2 times the amount of time. All right. So we just replace, t with 4.2t, distribute the square to the 4.2. 4.2 squared is going to give us 17.64. 1/2 at squared in black is our x value, so I'm going to factor out the 17.64 in the front. I'm going to carry the 1/2 at squared in black just right behind that, but I can substitute 1/2 at squared for x. Hopefully by now the stuff gets boring, and therefore our answer is just 17.64x. Okay, I hope that helps. You can use this strategy as long as you substitute in the right variable, have good habits, use parentheses, make sure you distribute the exponent properly, and you should always arrive at the proper, aka correct coefficient for these types of ratio problems. All right, good luck, stay nerdy, don't be whack.